Welcome back, my steel design friends. In this video, we're going to show you how to design for column base plates. In order to transmit column loads into a foundation or into a support, we have to have a way to spread these large concentrated forces out over an area so that we don't fail the surface underneath, whether it's soil or whether it's concrete or whether it's even another piece of steel. There are calculations that we have to do. And in this video, I'm going to show you how to do it. So without further ado, let's get started. So the criteria that we're most concerned about in here is we're looking at axial loads on members, and in particular we're going to be looking at column base plates for axial compression. The section where this is located, it's actually in not so much a lettered section, but you'll find the criteria here on page 14-4 of the code. So if I zoom out just a little bit, and you can see everything that we're doing is falling down into this region, and it has to do with trying to figure out what are the dimensions of this plate such that if I have an axial load acting on this column, what do the dimensions of the plate need to be in terms of the width, the height, and even the thickness is a factor in it. And so there will be a couple of equations that we'll look at, and I'll spell out the graphics a little bit better, but the majority of the information that we're looking at is going to revolve around this picture here. So I'll redraw this a little bit and we'll take a note of it. But otherwise, it's pretty easy. We're looking at column base plates for, in this case, W sections or S shapes, I-beams, if you will. And so we know we've got dimensions of BF and a depth associated with that section, and then we're going to kind of define a critical region on this that will help us to get the dimensions capital B and capital N of this plate. And there will be some other criteria that isn't handled in this book that kind of comes from a fabrication standpoint that we'll also talk about as we kind of try to get our factors squared away as we start to try to look at those. So let's take a look at what we have happening here. All right, so what we're looking at is some of the design considerations that we have are that we're looking for the area of the plate depending on strength of the supporting material. So again, what is the allowable pressure that can be held up? So if it's concrete, we're talking about the 28-day compressive strength F prime C. Maybe it's 3,000 psi, maybe it's 4,000 psi. If it's soil, maybe it's something a whole lot less. A sandy foundation or something like that. We've got to get a bigger plate to get that load spread out to get the stress under the plate a whole lot less. If it's something like steel, it's a lot stronger. Maybe I don't need as much of a section. And we'll get into steel bearing plates when we start looking at beam bearing conditions here later on in our series, but we're not quite there yet. So that's how we're going to size the plate dimensions based on the bearing stress. Okay, the thickness is going to be controlled by some aspect of bending within the plate, and I'll show you the locations in which we're looking at for when we get to that. And there are a couple of different checks that we need to do. Okay, now typically what you'll see is that column bearing, the column and the plate itself are usually one solid entity that's fabricated in a shop or something. The columns ship out to the website, to the job site with a base plate already pre-welded onto it, so that it's just basically a solid assembly. Now, one of the things that you have to be concerned about when you do that is what happens if, normally we picture a column being perfectly vertical, but in fabricating, it's possible that we don't quite get a square cut on this thing and this plate gets inclined. And so what they do is they actually, a lot of times, will mount this plate so that it's not technically sitting on the surface. There's actually a little bit of a gap in between. And so if this is my anchor rod that's coming up out of the foundation, and then there are holes in the plate where this passes through, normally you think of this as, well, I'm just going to put a nut on this rod and hold this thing down on the foundation and we're good to go. But if this thing isn't square, in order to be able to get this, column perfectly vertical, we don't really care what the plate is doing. It's the column that needs to be correct, because that's the one that has the holes and the assembly parts for the beams and the girders that are coming into it. So what they will do is they will put a secondary leveling nut on the rod underneath the plate and set it to a certain position, and then they'll set the column down on top of it. Okay, and then they'll adjust these nuts on the bottom side of the plate so that they can kind of tilt this thing and level it, so that, if my column is leaning, I'm going to tilt it so that it starts to, like this, so that my column is now vertical. At the end of the day, that's all I'm worried about, is this thing being vertical. And so these are, what we call leveling nuts or leveling screws or something like that. And then once that's set, they'll come in and they'll put a nut over the top of this thing just to hold it and kind of hold it and lock it in position. The gap then is filled with some sort of grout or cementitious material in order to fill the void and, again, allow all of that load that's coming into the column to get passed through the plate into the grout, which then loads the concrete down below. It's all kind of the same idea. So, there's getting this grout layer installed correctly without holes or any pores or anything, air pockets, is a very critical issue. Okay, normally this is a very soupy material, very liquid, not quite a liquid, but it's liquid enough that it free flows, that it will flow and fill those holes very well or very easily. But that's kind of the leveling mechanism that we're looking at. Okay, now the way that we design these plates, it comes from kind of a basic mechanics materials approach. Now the considerations we're designing this plate for are for axial load only. There's no bending or overturning happening on this. Okay, so if we assume that the plate is centered on the column, then the pressure that's felt by this plate, this is going to be some sort of normal stress. That's going to be the amount of the factored load divided by B divided by N as we start to calculate that value. And this is what we're going to be comparing to our stress. Okay, so that's how we're going to size for B and N. Now, what happens with the plate to size for the thickness is we have to consider, well, where are the critical sections and how is the thickness determined? Well, it turns out that if you look at this and if you draw, say, a critical section at the edge of the flange, you have some load acting on this plate. The load pushes down, the pressure pushes back, and we actually get kind of this cantilever effect on the end of this plate that will cause this end of this plate to bend up. And so there's a critical section that exists somewhere near the edge of the flange. And if I look at the other direction on here, so what we're looking at is that there's a critical section that occurs kind of down through this area. Okay, but I could also get the case where this guy is the one that controls. And typically the longer this dimension is, the more likely it is to control on the size on the thickness and the bending stresses associated with that plate. So to help us with these calculations, we're going to define a few dimensions on our plate. Okay, so we know for our I-beam that we have a flange width of BF and we have a depth of beam that is D. Okay, and so for a plate that is centered on this column, we're going to call the width as capital B. Again, I just associate capital B with the flange dimension, and then capital N goes with the depth dimension. Okay, I'm not sure why they use those letters, but that's the way that the code does it, so that's the way we're going to do it. Okay, now, there are some other design considerations we have to look at that in order to accommodate anchor bolts that are outside of the web, normally you need, something like 2 inches from the edge in order to be able to physically provide enough room for the hole and a washer and a nut to land on top of it and still be in full bearing on the plate. So normally one way that you can kind of get a quick size guesstimate for this plate is to take the depth of the beam and then add basically 4 inches on this side and 4 inches on this side. That gives you plenty of room to get the hole in. Again, this is a rule of thumb. You still have to confirm everything. But if I'm just trying to get kind of a rough size of what this plate is and is it going to be a problem for my loads on it, that I can get kind of a quick guesstimate on the size of the plate based off of this add 4 here, add 4 on the bottom. And then of course you add 4 on the sides as well to kind of get those dimensions. Again, it's kind of a rough check that we're going to look at. Now, this failure idea that we have that, I had a failure plane going through here and I had a failure plane just on the edge of the flange. It's not exactly at the edge. It's actually inset a little bit. Okay, and so if I draw those lines, there's this critical boundary that develops that, and again, we're looking at kind of an I-beam happening here, that my dimensions, we're going to call the width of this guy. And again, we're looking at the orientation as though it were an eye. If I kind of do this to, my pencil head broke. If I'm looking at, kind of something that looks like that as my eye on there, the critical width of this side is going to be measured as 0.8 times BF. Okay, the width of the flange. So it's inset a little bit. And then the critical dimension for the vertical side of this critical region is taken as 0.95 times D. Okay. All right, so these quantities you can calculate based on the column. Okay, the dimensions then that we need to find and the parameters that you use for design are these little m, which there's 2 of them, one on either side, the 0.95D and a little n that's on either side of the 0.80 BF. Okay, and those guys are calculated according to the section in force transfer on the page that I just showed you. M and N are those criteria that will help you figure out what B and N should be. And then, well, once you choose a plate dimension, then I can calculate what the corresponding M and N is, and then those guys are used then to calculate the thickness of the plate. Okay, and I'll show you how to do that here in an example in just a moment. Okay, all right. So there is another criterion we'll talk about momentarily. It's called the lambda in prime criterion, which is these other two formulas, and I'll explain those in just a second. But then if you flip over one page, this is where you figure out how thick the minimum thickness of plate that you need is. And you can see that it's an L parameter, which I'll explain that in a sec, 2 times PU over 0.9 FYBN. There's your yield, that's your phi factor, okay? And then my yield stress, and then B times N. So the size of the plate greatly affects the minimum thickness that you're allowed to have, okay? And so that's how we start to kind of size all of these for this. So this is where the thickness equation is going to come from. Okay, so that's our kind of our basic guidelines for what it is that we're trying to do. Okay, now the actual specification for this, okay, there are some checks that we have to do in order to compute the capacity of what this column can do, and those occur back in the specification in section J8. Now, normally J8 is controlled by, is what you're looking at when you're looking at connections, bolts and welds and those kind of things, but it's also for load transfer between members, kind of bearing criterion. So J8 is the column bases and bearing on concrete. Now you can see that phi for this is going to be 0.65. It's one of the lowest phi values that you'll see. And part of that has to do with the fact that you're bearing on concrete, and where we were using phi of 0.9 when steel yielded because it was a very ductile failure. When concrete fails, generally it's a very destructive and very dangerous situation when cracks and things can form in concrete. And once you crack concrete, you cannot uncrack it. Okay, so that's why this value is really, really low for our phi value. Okay, so once I have that, then the nominal capacity equations then are located here. Okay, and then we're looking up at 16.1-141. This is where the equations are all at. Okay, and so we have our capacity, for two different cases that we'll have to check, and I'll explain these in a second. And there's some A1s and A2s that we need to kind of define, and that's the hardest part of this whole process. Otherwise, it's pretty much a straightforward situation. Okay. All right, so that gets us our pages for that. Okay, so if we come and we look, here are the two formulas, and I'll kind of try to illustrate what it is that they're drawing on this. Unfortunately, even though that was a specification on there, there isn't much in the commentary. It basically says, yeah, this section conforms to ACI, and that's all it says. So you can't go get extra information about this, unlike some of the other steel-related areas. They're deferring to the ACI code in order to design the foundation on this. But there are two different criterias. Those two equations I showed you, equation J8-1 and J8-2. Okay, and so for the nominal strength, which is called as P sub P, okay, when the bearing is on a full area of support, P sub P is taken as 0.85 F prime C times A1. Okay, now this 0.85 F prime C is a very common allowable stress in concrete design. In fact, if you do the Whitney stress block, you will see this combination used over and over, 0.85 F prime C. Okay, so that's just kind of an allowable compressive stress that the concrete can take. F prime C is the 28-day strength, okay, which is the main specification for when you place an order for concrete. Okay, and we're going to take 85% of that value as the allowable stress on this. Okay, A1 is the area of the base plate. Okay, so that's my capital B times my capital N. Okay, so when we talk about bearing on the full area of the support, we're talking about a situation in which we have something like a pedestal or something, and this section is sitting up on this pedestal and it's roughly matching the dimensions of the plate. Okay, because what happens is that this area becomes the limiting value, and then once you get down, if you can get the load through that block, then it becomes a different type of calculation than what I'm going to show you on the other case. Okay, so that's how we figure out the concrete pedestal situation, and for case number one. For case number two is a situation where the bearing on A1, which is less than the full area of the concrete support. So now we have a concrete slab and a plate where this is bearing directly on it, and what happens is the critical stress is assumed to occur at some sort of 45-degree angle, and you'll actually use a dimension in concrete to, of this width to help figure out what the stress is as it fans out and spreads out from the load going in. So we got to be kind of careful on that. A1 is still B times N, but A2 is called as the area of the supporting surface that is geometrically similar and concentric with the load area. Okay, so if I look at this from the side, we can see that if I put a plate that is close to one edge, all of the material on the slab over here does nothing to help with the load. We have to consider that I take this dimension and I double it, and that becomes the width of the concentric area. That the center line of the column has to line up with the center of this area, and this is the area that's responsible for resisting the stress. All right, now I know that picture is a little confusing. Let me show you another version of it and kind of get a sense of trying to weigh it is. So let's consider that, you know, a big slab here, and I'm not going to draw it as an I-beam. I'm just going to draw kind of your column area that's here, and it's located a distance of L1 from one edge. Okay, well, the concentric width associated with that then is another L1 this way. So the shaded region, this big shaded region here is what I'm calling as A2. Okay, and then relative to the center of the column, I have, you know, two possible dimensions. I have an L2 up here and an L3 here. So the area, this concentric area that we're calculating is going to be 2 times L1, 2 times this guy, the edge distance, multiplied by the smaller value of L2 and L3. Okay, so if this is 3 inches and this is 10 inches, your concentric height is going to be equal to then, you know, double that value. Okay, and I've left off another 2 because it is double the smaller of those two values. So it's basically 4L1. If I write this out, it's 4 times L1 times the minimum of what we're calling is L2 and L3, the dimensions on this. And that's how you can calculate the area, the A2 dimension for an area that is concentric. So to give you some idea, you can see what happens if I put this column up in the corner. You know, I still play the same game this way, but then now I've got a much smaller area. This is a much higher stress situation than this guy just by moving this plate. So anytime you start getting columns out towards the corners, generally you've got to be very, very careful on the stresses and what the limits are for those calculations. So that's kind of this idea of what A2 is a reflection of, you know, the load and the area that is concentric with that load. So you can kind of reason your way through it a little. Maybe it's a little bit more clear than what these calculations are. Okay, but in either case, the area A2 is concentric with A1, but bounded by the slab edges in all cases. If you're out here in the middle, I mean, you may get the majority of the slab to work for you, and that's a good situation. But if I start creeping it over to the edge, that A2 value starts to decrease. Okay, so that's what we're looking at on that. Now let's flip back to the page, because there is one other issue on this. That the code says that the capacity is going to be 0.85 F prime C, there's that compressive strength again, times A1 times the square root of the area A2 over A1. Okay? And so what we could look at doing is we could say, well, you know, if I play with these parameters a little bit, you know, I could drive this number to one extreme or the other depending on what I do with A1, right? If A2 is really, really small, then I have a very small load. But if I go and put this thing on a massive slab of, you know, large dimensions for A2 on there, well, there's kind of a practical limit that starts to kick in. And so they're going to bound the upper limit of this as 1.7 F prime C times A1 as the maximum. So you can see that when I'm bearing directly on the slab, this upper limit is basically double what the other one was. Okay, so what we're looking for is to get to the maximum load that you can have, you would optimize such that the square root of A2 over A1 would basically be a value of 2. That's kind of your optimal limit for what's happening here as you're looking at. But usually you don't have a lot of control if this thing lands where it lands, but that's how we start to calculate. A1 is still B times N, A2 is the area again of that concentric load that we have here. Okay, all right, now, so if we go back and we look at our first picture, the parameters that we need in order to size the thickness, if I come back to this, we're after little n and little m. Okay, so if I know that this whole dimension here, from here to here is capital N, and I know from here to here is capital B, and I've chosen that based off of the strength calculation. I can then figure out what the corresponding little m and little n values are. And so that's what you're seeing on the formulas on this page. All right. The little n then is just basically going to be capital B minus 0.8 BF over 2. And little m is going to be n minus 0.95 times d over 2. And then once I have those guys, okay, we're going to choose the larger, okay, and we're going to call that as a parameter. That's that little L that I showed you in the formula for the thickness. Okay, so you choose the larger of the two. Actually, you choose the larger of these two plus another one, but this is for the flexural case for the cantilever ends, the bending capacity, and what the minimum thickness is. So they do kind of a strength calculation here based on the load that's applied, the area of the plate, and then that L dimension. So it's L times the square root of 2 pu over 0.9 FYB times n. Okay, where L is the larger of the m and n parameters that are coming out of this. So you're going to choose the B and the N, and then we're going to work off of that. So that's how you get the thickness of the plate. Now, there is one other situation that we've got to kind of look at, okay, and I'll show you how we handle that. And this is what we call the lambda in prime criterion. Okay, so we originally designed, chose our section such that there was a critical boundary whereby this plate wants to flip up, or wants to flip up this way, or the bottom wants to come this way, or the bottom wants to come this way, based on the pressure that's being spread around. Okay, what can happen, especially with shapes like this, where I have, it's not a tube steel section, but it's an I-beam. If we look, imagine that I'm going to draw this kind of in an orthographic view, that you have a uniform pressure based off of the load that's acting on area BN. This is your area A1. Okay, and then all of that load's coming through the column, and it's pushing down at the flange and the web locations. Okay, so if you consider this, okay, that there is a region between the flanges and the web that kind of experiences, a complex plate bending behavior. I mean, imagine, if I draw this a little bit closer, here's the edge of the flange, here's the edge of the web, and here's the edge of the bottom flange. It's this region kind of in between that is an issue. Okay, and now again, what's happening is I'm putting pressure all over the entire bottom edge of the plate. So if you consider this is a boundary, and this is a boundary, and this is a boundary, you basically have a plate bending problem that's bounded on three sides, but it's free to do whatever it wants on the other. So if I draw this kind of so you can visualize what's happening due to the load, because the load is over everything on the bottom here, you can kind of see that, okay, well, these three edges are going to be held in place by the load from the column itself, but this edge that kind of spans between the ends of the flanges is going to have the ability to kind of flex and bow up. Okay, so I mean, if you take if you've ever taken a sheet of paper and you grab three edges of it, and then you put some sort of load on it, that fourth edge wants to curl, right? It doesn't hold perfectly straight. So there's some flexing or some flexure that happens, kind of a two-dimensional or two-directional flexing problem that starts to occur on this. And that's what we're looking at on trying to calculate this, the stress that we're looking, and I believe it's a St. Venant's principle for stress that governs this kind of plate bending theory that's happening. So that's the lambda in criterion. So I'll show you in the example how we calculate that. But for now, I want to go straight into our calculation or our example and kind of illustrate the process, and then we'll add that lambda in criterion. Because often it doesn't control, it can, but it's not the biggest things. All right, so let's kind of work through our problem here. Okay. And so here's what we have. We're going to look for a preliminary base plate for a W14 by 145 column of, I have A36 for this. Let's see, 3 KSI, just double checking something real quick. Yeah, 36 KSI. Not a real common grade of steel for this column, but the process is still the same. These formulas have been around for a while, so this problem is a little bit dated. The column dead load is 400 kips. The column live load is 275 kips. And I know from the manual, I can look up the dimensions for the W14 as being a BF of 15.5 and a D of 14.78. Okay. The 28-day compressive strength of the concrete is said to be 3,000 or 3 KSI or 3,000 PSI. So that's a specification for the strength of the bearing surface. And so we want to figure out what size of base plate do I need to get this column safely supported by that piece of concrete. Okay, so first thing we do, factor the loads, 1.2 dead plus 1.6 live. If I plug those numbers in, I get 920 kips is the axial load, factored load that's on this. All right, so what we're going to do is we're going to take a guess and we're going to assume that it's concentrically aligned with this plate. So we're going to figure out, well, what is my A1 minimum dimension that I have to have for this? All right, and we're going to take PU, we're going to divide it by phi of 0.85 F prime C. Okay, and so if I plug in all my values, phi is 0.65, there's my 0.85, there's 3 KSI, 920, and if I do that, my entire, my A1 area is 555 inches squared. Okay, now again, for base plates, we typically guess 4 inches larger on each side than the column dimensions. This allows for the bolts. We've talked about that. But if I take B times N and set it equal to 555, and if our dimension of plate B is approximately equal to N, then B squared is equal to 555. B is going to be 23.5 inches. Okay, now one of the things that we want to be careful of with particular to plate sizes, and now again, what I've and this is, we've changed this. This was for an older code version, so we're not going to look at that guy. Okay, we're going to actually use the dimensions of 24 by 24 on this. We're going to round this guy up to the nearest inch. Now, that's B times N if it's a square plate. Now, in cases where you have taller flange or taller beams than you do width of flange, what you want to try to avoid doing is having plates that are very close in dimensions but not the same, right? Because if I have a plate that is 24 inches wide and 22 inches tall on this, in order to accommodate this beam, this is a hard dimension for a fabricator to visually see. You know, they go through and they cut the plate, and unless they mark it as this is the 24 dimension on the ground, these are hard to distinguish. Whereas if you had a plate that was 16 by 24, you could see a drastic difference. This, and this is speaking from experience, I've had plates get welded on in the wrong orientation, right? So what they do is that when they fabricate these plates, there's one guy that's cutting the plate to the shape he needs and another guy that's putting the holes in, and then there's a third guy or group that is welding this plate onto the column. So if this is 24 by 22, it's real easy to get this thing turned the wrong way. Okay, and then when that happens, your bolt holes won't line up with the anchor bolts in the bottom. So kind of as a rule of thumb for most column base plates, I typically make them square so that the orientation doesn't matter. Okay, so they put the 4 holes into the plate. However this plate is oriented on this thing, it will always be right and can still work for us. Okay, so square plates are definitely preferred, okay, just because of the fabrication issues. All right, so anyway, that's a little side thought on considerations when I'm designing this. All right, so let's go see if we can figure out what the thickness is based on the little n and the little m criteria. This is just a straight plug and chug. Little n is b minus 0.8 bf divided by 2. Okay, and so that's going to be 24 inches minus 0.8 times the 15.5 divided by 2. If I do that, this is a 5.8 inch value for a little n. Okay, I'm getting a little bit of glare on this. There we go. That'll help. Okay, and then my little m is going to be big N minus 0.95 d over 2. Okay, and so that's 24 minus 0.95 times 14.78 divided by 2. I get a 4.97. Okay, and so to size for the flexural case, we're going to choose the larger of these two values. Okay, the larger of m and n. So L, my L parameter is going to be the larger of these. It will be 5.8 inches. If you look at what we have happening there. Once I have that, then I can jump down and I can calculate the thickness using my formula here. You know everything now. So this L parameter is 5.8, and then I do the square root of 2 times PU. So that's 2 times 920. Okay, all over 0.9, all over 36 KSI, all over 24. So again, we're doing 24s here, not 25s on this. Okay, and so when I do that, then the T minimum is 1.82 inches. Now that you can't specify a plate exactly that thick, so we usually round it to the nearest nominal thickness, which for a 1.82 inches, the most common size larger than that, the next larger one is generally a 2-inch thick plate. Okay, so column base plates, especially for these big loads, can be very, very, very thick. A 2-inch plate is a very thick plate. All right, now let's take a look and see what do we do with that lambda n prime criterion. Okay, and then we'll conclude this section. All right, so if we go and want to consider the lambda n prime criterion, the formulas that were in the specification are as follows. Lambda is equal to 2 times the square root of x over 1 plus the square root of 1 minus x, and that's less than or equal to 1. Okay, and so conservatively, the code says you can take lambda as 1 and not do this calculation, but you may pay a price on the on the thickness. Okay, the x parameter in this equation is given as 4 times d times bf all over d plus bf quantity squared multiplied by the ratio of pu to phi p sub p. Okay, and so this will be my, that's a 0.65 for my phi value. And so I just basically plug in and check all of this. And if I do this number should be somewhere around 0.817. Okay, in fact, let me double check that number now that I think about it. All right, so there was a little bit of an issue. First one was that I was using the old phi value. The current phi is 0.65. The other one was I was using the old b times n value of 25. Okay, in reality, it should be 576 or b times n. Now, the good news is that the difference, the old number was 0.817. The new number is 0.819 for those factors. So this is 0.819 is what we're plugging into there. So it's basically no difference on that. So it's pretty well set on that. So anyway, we're going to take a look at those values. So if I go through and I plug in this 0.817 number, it's basically, like I say, it's a little bit off, but it's close enough to illustrate the process. I do 2 times the square root of 0.817 all over 1 plus 1 minus 0.817 less than or equal to 1. And then this is going to... All right, that was my son who said hello. So, all right, back at it. So here's lambda. This is good. So we can calculate our lambda value, and you can see that 1.807 over 1.43 is what these quantities are. If this had been the 0.819, this would have been slightly larger. 1.6, yeah, 807. Okay, and so this is going to be less than or equal to 1. Is bounded by this. This limit is clearly greater than 1, so it didn't matter, this change that I had over there. So we're going to use a lambda of 1.0, which we could have assumed in the first place, but this proves the calculation. So we're actually using a conservative value. So once I do that, then you can calculate n prime as being 1 over then 1/4 of the square root of d times bf. Okay, and so if I do that, the n prime parameter is 3.78. So then lambda n prime is 3.78. And so all we do then is we modify our selection of the larger of m and n and ln prime. Okay, so if I choose the larger of these, clearly my 5.8 is still controlling, which is what we had in the last calculation. It's the same as before. My thickness of my plate will be 2 inches on that. All right, now for cases with anchor bolts, what you're going to see is there's some different arrangements and kind of some general thoughts as we conclude this. The calculations are very straightforward. I mean, you can pretty much build a spreadsheet and plug in the values and boom, you've got all of that. Okay, but if I go through and I look at this, some things to kind of keep in mind. If I have a plate for an I-beam where the bolts are outboard, okay, typically the m and n dimension will control, and that's what we just saw. Okay, so L is either equal to m or L is equal to n usually controls. If my plate is much smaller and it's tucked in pretty tight and I don't have that 4, because remember we added approximately 4 inches outside of that dimension in order to be able to accommodate the anchor bolts outboard. If for some reason it is a smaller connection and your holes are here in the web and I pull these plate dimensions in such that m and n are really, really small, those are the cases where the lambda n prime criterion can start to control. So this is why you still need to do the check, even on the case where the bolts are outbound, but most of the time you can see it wasn't even really close when we did the calculations. It was 4.97, 5.8, and this lambda n prime was 3.8. It's a very small value. But if these two guys start getting really, really small, then this guy can start to control, and that's the phenomenon where this happens usually, where the bolts are inbound or inboard of the I-beam. And we do this on very compact connections and footing bearing plates for those kind of things. So anyway, that's what we're doing. And so those are kind of some closing thoughts on our L parameter. So I hope that's made sense to you as we start to kind of look at our calculations. It's a very straightforward process for sizing a plate for a concentric axial load. I hope that's made sense to you. As always, if you've got any questions, toss us some comments down below. And as always, if you found this useful, please be sure to like and subscribe to the channel, and we'll keep these lessons coming to hopefully help you, expand your steel design expertise. That's my goal here. So with that being said, I wish you all a wonderful evening, and we will see you guys next time. Bye.